Hello, I'm Mikko Lempinen, and in this video we're diving into how LLMs, these modern text-based AI models, craft sentences that are not just coherent but remarkably human-like. At their core, large language models are a subtype of machine learning models designed to understand, generate, and sometimes even anticipate human language. Born out of immense datasets and consisting of billions of parameters, these models crunch numbers at an astonishing rate to predict the next word in a sentence. Let's break that down. Imagine you're playing a game where you have to guess the next word your friend is going to say. With enough time spent with them, you start understanding their speech patterns. That's somewhat similar to how LLMs learn over time from vast amounts of text data. How exactly does an LLM spit out whole, coherent sentences? It all starts with an input, often a prompt devised by a human user. The model then processes this input through what's called a decoder, which is part of the transformer architecture, that is essentially a sophisticated guesser that has learned from its training data how to follow up on any given input. In this illustration of a neural network, the transformer is included within the hidden layers. The decoder predicts one word at a time based on probabilities, choosing the most likely next word until it forms a complete sentence that makes sense in the given context. This is known as autoregression. In the context of large language models, parameters are akin to the knobs and settings on a complex machine. Each parameter holds a numerical value that determines specific aspects of the model's behavior, like how much emphasis to give to certain words or patterns in sentences. In this diagram, each of the connections between neurons can be thought of as a parameter. In reality, calculating the amount of parameters is a bit more complex, but roughly speaking, by calculating the amount of these connections tells us nearly the amount of parameters a neural net has. You can imagine each parameter as a tiny instructor guiding how the model should interpret and generate language. With billions of these instructions, LLMs can finely tune their outputs to mimic human-like text with emphasis on the word mimic. The total number of parameters thus plays a crucial role. More parameters generally mean more capability to learn nuanced differences in language, but also require greater computational power and more data to train effectively. To become adept at autoregressively predicting suitable words for a sentence, LLMs undergo a rigorous training regime. They are fed terabytes of text from books, articles, websites, and more to build their understanding. They learn not just vocabulary and grammar, but styles, tones, and even idiomatic expressions. The training phase is critical. It uses techniques like unsupervised learning, which allows the model to explore text and self-improve without explicit feedback, and supervised learning, where the model is corrected when it predicts wrong. The diagram here shows the general pipeline of training an advanced LLM. Once a base LLM is trained on a broad dataset, it can be fine-tuned to excel in specific tasks or understand particular kinds of language. This process involves additional training, typically on a narrower dataset relevant to a specific task or domain. For instance, if you want an LLM to function as a chatbot and answer the user's queries, you would fine-tune it with conversations between a user and an assistant. This helps the model understand the formats, nuances, and terminologies typical of user-chatbot interactions. Fine-tuning allows users to customize the general prowess of an LLM to their particular needs, making it more effective and efficient for specific applications. Now you should have a general idea on how large language models function and spew out human-like text. Thank you for watching.